ECDSA in P2PKH transactions. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring the critical role that the elliptic curve digital signature algorithm, or ECDSA, plays in Bitcoin's P2PKH transactions. ECDSA is the cryptographic heart of Bitcoin's security model, providing the mathematical foundation that enables secure, trustless transactions without relying on any central authority. Understanding ECDSA is essential for truly grasping how Bitcoin achieves its security guarantees. It is not just about knowing that signatures exist. It is about understanding the mathematical principles that make it computationally infeasible for anyone without your private key to spend your Bitcoin. These same principles simultaneously make it trivial for anyone to verify that you authorized a transaction. ECDSA achieves this remarkable balance through the properties of elliptic curve mathematics. In this presentation, we will use detailed sequence diagrams to visualize exactly how ECDSA operates within P2PKH transactions. We will trace the flow of data from the moment you decide to create a transaction, through the signature generation process, the broadcast to the network, and finally, the verification performed by nodes. These diagrams will help you understand not just what happens at each step, but also the order of operations and how different components interact with each other. We'll explore the SECP256K1 elliptic curve that Bitcoin uses, understand why this particular curve was chosen, examine the mathematical operations involved in key generation, signing, and verification, and see how ECDSA integrates with Bitcoin's scripting system to create a complete security framework. By the end of this presentation, you'll have a deep understanding of how ECDSA makes Bitcoin secure and why this security model has proven so robust over Bitcoin's history. ECDSA fundamentals. The elliptic curve digital signature algorithm is a variant of the digital signature algorithm that operates on elliptic curves rather than finite fields. This might sound abstract, but the practical implications are significant. ECDSA provides the same level of security as traditional DSA or RSA with much smaller key sizes. Where RSA might need 3072-bit keys for strong security, ECDSA achieves comparable security with just 256-bit keys, making it ideal for a blockchain where every byte matters. Bitcoin specifically uses the SECP256K1 elliptic curve, which is defined by the equation y squared equals x cubed plus 7, all modulo a very large prime number. This curve was chosen by Satoshi Nakamoto for several reasons. It has efficient implementation characteristics. It was a standard curve published by Certicom in the Standards for Efficient Cryptography, and importantly, its parameters were generated in a verifiably random way, reducing concerns about potential backdoors. The SECP256K1 curve has a generator point G, which is a specific point on the curve that serves as the starting point for all key generation. The curve also has an order n, which is the number of points on the curve. This order is a prime number slightly less than 2 to the 256th power, which means there are approximately 2 to the 256 possible private keys, an astronomically large number that ensures security. ECDSA's security rests on the elliptic curve discrete logarithm problem, or ECDLP, given a point q on the curve that was created by multiplying the generator point g by some scalar value k, where q equals k times g. It's computationally infeasible to determine what k was, even though anyone can verify the relationship. This one-way property is what makes ECDSA secure. Your public key can be freely shared because no one can work backward to find your private key. The mathematical operations on elliptic curves involve point addition and point multiplication. Point addition is defined by drawing a line through 2 points on the curve, finding where it intersects the curve again, and reflecting that point across the x-axis. Point multiplication, which is repeated point addition, is what we use to generate public keys from private keys and to create signatures. These operations have the crucial property that they are easy to compute in one direction but hard to reverse, which is the foundation of all public key cryptography. Key generation process. The journey from a private key to a Bitcoin address involves several steps, each serving a specific cryptographic purpose. Understanding this process is crucial for grasping how ECDSA integrates into Bitcoin's overall architecture. The process begins with generating a private key, which is simply a random 256-bit number between 1 and the curve order n-1. Generating a cryptographically secure random number is actually one of the most critical steps in the entire process. If your random number generation is flawed, predictable, or has insufficient entropy, an attacker might be able to guess or brute force your private key. This is why Bitcoin wallets use operating system-level cryptographic random number generators or hardware random number generators that gather entropy from physical processes like thermal noise or timing variations. Once you have a private key, generating the corresponding public key is straightforward but computationally intensive. You multiply the generator point G by your private key using elliptic curve point multiplication. This operation involves hundreds or thousands of individual point additions depending on the value of the private key, but modern computers can compute it in milliseconds. The result is a point on the curve with x and y coordinates, each 256 bits long. The public key can be represented in two formats, uncompressed or compressed. An uncompressed public key includes both the full x and y coordinates, which totals 65 bytes when you include the prefix byte. A compressed public key includes only the x coordinate and a single byte indicating whether y is even or odd, which totals 33 bytes. This works because for any x coordinate on the sect P2PKH curve, there are only two possible y coordinates that satisfy the curve equation, and they are reflections of each other across the x-axis, meaning one is even and one is odd. The public key then undergoes hashing to create the public key hash that appears in P2PKH addresses. First, SHA-256 is applied, producing a 256-bit hash. Then RIPEMD160 is applied to that result, producing a 160-bit hash. This double hashing serves multiple purposes. It shortens the address, provides additional security through defense in depth, and as we discussed earlier, offers some protection against quantum computers as long as the public key remains hidden behind its hash. ECDSA signature components. An ECDSA signature consists of two numbers, conventionally called R and S, each being two 56-bit integers. These values are mathematically related to both the message being signed and the private key, but they do not reveal the private key itself. Understanding what these values represent and how they are generated is key to understanding ECDSA security. The R value comes from a random number k, often called the nonce, though this term is slightly misleading since k must never be reused across different signatures. To generate R, you first generate a random k value between 1 and the curve order n. You then multiply the generator point G by k to get a point on the curve, and R is simply the x-coordinate of this point, taken modulo n. So R equals the x-coordinate of the point k times G, modulo n. The S value is where the private key and message hash come together. The formula for S is S equals K inverse times the quantity message hash plus R times the private key, all modulo n. This formula is carefully designed so that the signature can be verified using only the public key, but cannot be created without the private key. The K-inverse term is the modular multiplicative inverse of K modulo n, which is a number that when multiplied by K gives 1 modulo n. The criticality of K's randomness and uniqueness cannot be overstated. If you ever reuse the same K value for two different messages with the same private key, an attacker can solve for your private key using simple algebra. This is exactly what happened in the Sony PlayStation 3 hack. Sony's implementation used a static K value, allowing hackers to extract the signing key after observing just 2 signatures. Similarly, if K is predictable or has insufficient randomness, attackers may be able to recover the private key through various cryptanalytic techniques. To address these concerns, modern Bitcoin implementations use deterministic K generation according to RFC 6979. Instead of generating K randomly, it is derived deterministically from the private key and message hash using HMACSHA 256. This ensures that K is different for every message, appears random to anyone without the private key, and is always the same if you sign the same message multiple times with the same key. This deterministic approach eliminates the risks associated with poor random number generation while maintaining all the security properties of ECDSA. Transaction message hash creation. Before we can generate an ECDSA signature for a Bitcoin transaction, we need to create the message hash that will be signed. This isn't as simple as hashing the entire transaction. Bitcoin has a specific procedure for constructing the data that gets signed, and understanding this procedure is essential for implementing transaction signing correctly. The process begins with the transaction itself, but in a modified form. For each input that is being signed, we create a version of the transaction. In this version, that input script sig is temporarily replaced with the script pub key of the output being spent. This means we are signing a transaction that includes the spending conditions we are trying to satisfy. All other inputs in the transaction have their script sigs set to empty during this signing process. This approach prevents certain types of attacks. By including the script pub key in what we sign, we are cryptographically committing to the spending conditions we are satisfying. This prevents an attacker from taking our signature and trying to apply it to a different output with different spending conditions. Each signature is specific to both the transaction structure and the particular output being spent. The SIGHASH type is then appended to this modified transaction as a 4-byte little Indian integer. The SIGHASH type specifies exactly what parts of the transaction are covered by the signature. SIGHASH_all, which has the value 0x01, is the most common and means the signature covers all inputs and all outputs. This ensures that if any part of the transaction is modified, the signature becomes invalid. Alternative SIGHASH types like SIGHASH_none and SIGHASH_single provide different levels of commitment and are used in more specialized scenarios. This entire serialized structure is then hashed twice with SHA-256, a process called double SHA-256 that is used throughout Bitcoin. The first SHA-256 pass produces a 256-bit hash, and the second SHA-256 pass produces another 256-bit hash. This double hashing provides additional security against certain cryptographic attacks, particularly length extension attacks that could be mounted against single SHA-256. The resulting 32-byte hash is the message that will be signed with ECDSA. It is crucial that this message hash is created identically during both signing and verification. Any difference in the serialization, byte ordering, or which fields are included will result in different hashes, and, consequently, signature verification will fail. This is why Bitcoin's consensus rules specify the exact serialization format in precise detail, leaving no room for ambiguity or alternative implementation. ECDSA signature generation sequence. Now let's walk through the complete sequence of operations that occur when generating an ECDSA signature for a P2PKH transaction input. This process brings together all the components we've discussed: the private key, the message hash, the random K value, and the elliptic curve arithmetic that binds them all together. The process begins when the wallet software decides to create a transaction. The user specifies the recipient, amount, and the wallet selects appropriate UTXOs to use as inputs. For each input that will be signed, the wallet retrieves the corresponding private key from its key store. This might involve decrypting the wallet if it is encrypted, deriving keys from an HD wallet seed using BIP32 derivation paths, or retrieving keys from a hardware wallet. Next, the transaction is serialized in the specific format required for signing. As we discussed, this involves replacing the current input script SIG with the script pub key of the output being spent. It also means setting other script SIGs to empty and then appending the SIGHASH type. This serialization must follow Bitcoin's exact byte ordering and structure requirements. The serialized data is then double-hashed with SHA-256 to produce the message hash, the 32-byte value that will actually be signed. Now comes the ECDSA signing algorithm itself. First, the deterministic K value is generated using RFC 6979. This involves creating an HMAC-SHA-256-based key derivation from the private key and message hash. The derived K value is checked to ensure it is in the valid range between 1 and n-1. If not, which is extremely rare, the derivation continues until a valid K is found. With K in hand, the R value is computed by performing elliptic curve point multiplication. K times G equals a point on the curve, and R is the x-coordinate of that point modulo n. Then S is computed using the formula S equals K inverse times the quantity message hash plus R times private key, all modulo n. The modular inverse of K is computed using the extended Euclidean algorithm, which is an efficient way to find modular inverses. Bitcoin enforces what is called low S signatures as a standardization rule. Since S and n-S are both valid signature values mathematically, we always use the lower of the two to prevent signature malleability. If the computed S is greater than n divided by 2, we replace S with n-S. This standardization ensures that only one signature form is valid for any given message and key, preventing transaction malleability attacks. Finally, the R and S values are encoded using distinguished encoding rules, or DER format. DER is a specific way of encoding data structures that ensures unambiguous representation. The signature gets wrapped in a sequence structure with type tags and length fields. The SIGHASH type byte is appended to the end of the DER encoded signature, creating the final signature that goes into the script SIG. This entire process is repeated independently for each input in the transaction. ECDSA Signature Verification Sequence. When a Bitcoin node receives a transaction, it must verify every signature to ensure the transaction is valid and the spender actually controls the private keys for the inputs being spent. The verification process uses only public information: the signature, the public key, and the message hash. Understanding this verification process is crucial for understanding how Bitcoin achieves decentralized consensus without trust. Verification begins when a node receives a transaction from a peer. The transaction is first parsed to extract its structure, inputs, outputs, version, and lock time. For each input, the node must verify the script SIG against the script pub key of the output being spent. For P2PKH inputs, this means extracting the signature and public key from the script SIG. The signature is DER decoded to extract the R and S values. The node also notes the SI hash type byte at the end of the signature, which tells it how to reconstruct the message that was signed. The public key is also extracted from the script SIG, and the node verifies that it is a valid point on the sect P2PKH curve. A point is valid if its coordinates satisfy the curve equation y squared equals x cubed plus 7, modulo the curve prime. Next, the node must reconstruct the exact same message hash that was signed. It takes the transaction and serializes it in the same way that was done during signing, replacing the current input script SIG with the script pub key from the output being spent, clearing other script SIGs, and appending the SIG hash type. This serialized data is double-hashed with SHA-256 to produce the message hash. If this process isn't done exactly the same way as during signing, the hashes won't match and verification will fail. Now comes the ECDSA verification algorithm. This is where the mathematical elegance of elliptic curve cryptography shines. The verifier computes two values. U1 equals the message hash times the modular inverse of S, and U2 equals R times the modular inverse of S, all modulo n. Then the verifier computes a point on the curve. P equals U1 times G plus U2 times the public key. This point addition is performed using elliptic curve arithmetic. If the signature is valid, the x-coordinate of point P, taken modulo n, will equal R. This works because of the mathematical relationship between the private key, public key, R, and S. When you work through the algebra, substituting the formulas we used during signing, everything cancels out perfectly and you get that the x-coordinate of P equals R. But crucially, this verification can be performed using only the public key, not the private key. If the x-coordinate of P does not equal R, the signature is invalid. This could mean someone tried to forge a signature without the private key, or it could mean the transaction was modified after signing, or there is an implementation error. The node also checks that both R and S are in the valid range between 1 and n-1, and that S is less than or equal to n divided by 2 to enforce the low S requirement. After ECDSA verification succeeds, the node continues with the rest of the script execution. For P2PKH, this means verifying that the provided public key hashes to the expected public key hash in the script pubkey. The public key is hashed with SHA-256 and then RIPEMD160, and the result is compared to the hash in the script pubkey. Only if both the ECDSA signature is valid and the public key hash matches does the script evaluation succeed and the input considered valid. Complete transaction flow with ECDSA. Let's trace the complete flow of a P2PKH transaction from creation through confirmation, focusing specifically on where ECDSA operations occur and how they integrate with the rest of the Bitcoin protocol. This end-to-end view helps solidify understanding of ECDSA's role in the overall system. The process begins when a user decides to send Bitcoin. The wallet software identifies available UTXOs that can be spent, meaning UTXOs for which the wallet has the corresponding private keys. The wallet constructs a transaction with inputs referencing these UTXOs and outputs specifying the recipients and amounts. At this point, no ECDSA operations have occurred yet. We are just building the transaction structure. Now comes the signing phase. For each input, the wallet performs the ECDSA signature generation process we described earlier. This involves serializing the transaction in a specific way, hashing it, generating the K value, computing R and S, and DER encoding the signature. Each input is signed independently with its corresponding private key. If a transaction has 3 inputs from different addresses, 3 separate ECDSA signing operations occur, potentially with 3 different private keys. Once all inputs are signed and the script sigs are populated, the transaction is complete. The wallet serializes the entire transaction into its final byte format, which includes the version, all inputs with their signatures, all outputs, and the lock time. This serialized transaction is then hashed with double SHA-256 to produce the transaction ID or TXID, which uniquely identifies this transaction. The wallet broadcasts the transaction to the Bitcoin network by sending it to one or more connected peers using the Bitcoin peer-to-peer protocol. Each peer that receives the transaction performs full validation, which includes verifying all ECDSA signatures. This ECDSA verification happens as each peer independently verifies every signature to ensure the transaction is valid before adding it to their mempool or relaying it to other peers. The transaction propagates through the network this way, with each node verifying signatures independently. This is a key aspect of Bitcoin's security model. There's no trusted party that validates transactions. Instead, thousands of independent nodes all perform the same verification, and they'll all come to the same conclusion because the math is deterministic. A valid ECDSA signature will verify correctly on every node. An invalid signature will fail on every node. Eventually, a miner selects the transaction from their mempool to include in a candidate block. The miner has already verified the signatures when the transaction entered their mempool, but they may verify again to be certain. The transaction is included in the block, and the miner begins proof-of-work computation to find a valid block hash. When the miner successfully mines the block, it is broadcast to the network. Other nodes receive and verify the block. This includes verifying every transaction within the block, and therefore every ECDSA signature. This means every signature, in every transaction, gets verified by potentially thousands of nodes. This redundant verification is what gives Bitcoin its security. No one can spend someone else's coins because they cannot produce valid ECDSA signatures without the private key. And every node independently checks these signatures. After the block is added to the blockchain and receives subsequent confirmations, the transaction is considered final. The outputs created by the transaction now become spendable UTXOs for the recipients. When those recipients eventually spend those coins, the cycle begins again with new ECDSA signatures proving their ownership. ECDSA security properties. The security of P2PKH transactions rests entirely on ECDSA's cryptographic properties. Understanding these properties helps explain why Bitcoin has remained secure despite being an attractive target for attackers, and why certain implementation details are critical for maintaining security. The fundamental security property is that the elliptic curve discrete logarithm problem is computationally hard. Given a public key Q that was generated as D times G where D is the private key, finding D is infeasible with current algorithms and computers. The best-known classical algorithms for solving ECDLP have exponential time complexity. For a 256-bit curve like SECP256K1, this means approximately 2 to the 128 operations would be required to find the private key through brute force, which is far beyond the capability of all computers on Earth combined running for billions of years. ECDSA signatures provide several key security properties. The first is unforgeability. This means that without the private key, it is computationally infeasible to create a valid signature that will verify with the corresponding public key. This is what prevents attackers from spending your Bitcoin. They can see your public key once you have spent from an address, but they cannot generate signatures that would pass verification without your private key. Second is non-repudiation. A valid ECDSA signature proves that someone with knowledge of the private key created it. You can't create a valid signature by accident, and you can't later claim you didn't create it if it's cryptographically valid. This property provides accountability and prevents disputes about transaction authorization. Third is message binding. An ECDSA signature is specific to the message being signed. The signature for transaction A cannot be used as a signature for transaction B, even if both transactions are being signed with the same private key. This prevents signature reuse attacks and ensures each transaction authorization is independent. However, ECDSA security critically depends on proper implementation. The most common implementation vulnerability is weak or reused K values. As discussed, if K is ever reused across different messages with the same private key, the private key can be extracted. If K is generated with insufficient randomness or in a predictable way, various attacks may be possible. This is why RFC 6979 deterministic K generation is so important. It eliminates these risks entirely. Another implementation consideration is timing attacks and side-channel attacks. ECDSA implementations must be designed to run in constant time, meaning they take the same amount of time regardless of the values of secret data like the private key. Otherwise, an attacker might be able to learn information about the private key by precisely measuring how long signing operations take. Modern Bitcoin implementations use constant time implementations of elliptic curve arithmetic to prevent these attacks. The hash function used to create the message hash is also critical. SHA-256 is cryptographically secure with no known practical attacks. If the hash function were weak and allowed for finding collisions, where two different messages produce the same hash, an attacker might be able to get you to sign one message and then claim you signed a different message with the same hash. Double SHA-256 provides additional security margin against potential future weaknesses in SHA-256. ECDSA versus other signature schemes. ECDSA is not the only digital signature scheme available, and understanding how it compares to alternatives helps explain Bitcoin's design choices and the evolution toward newer signature schemes like Schnorr signatures in Taproot. Each signature scheme has different properties, advantages, and trade-offs. Traditional RSA signatures, which are used in many systems like TLS certificates, rely on the difficulty of factoring large numbers. RSA signatures require much larger key and signature sizes than ECDSA for equivalent security. A 3072-bit RSA key provides roughly the same security as a 256-bit ECDSA key. In Bitcoin, where every byte stored on the blockchain has a cost, this size difference is significant. ECDSA's smaller keys and signatures make it much more suitable for a blockchain application. However, ECDSA has some limitations compared to other elliptic curve signature schemes. One major limitation is that ECDSA signatures are not deterministic in the same way that some other schemes are. Even with RFC 6979, you can't have multiple parties collectively create an ECDSA signature without complex protocols. This makes implementing multi-signature schemes with ECDSA challenging. Schnorr signatures, which Bitcoin adopted in the Taproot upgrade, address many of ECDSA's limitations. Schnorr signatures have a simpler mathematical structure that allows for signature aggregation, meaning multiple signatures can be combined into a single signature that is the same size as a single ECDSA signature. This enables more efficient multi-signature schemes and complex smart contracts. Schnorr signatures also have provable security properties and are non-malleable by design, unlike ECDSA, which required additional standardization to prevent malleability. So why did Bitcoin originally use ECDSA instead of Schnorr? When Bitcoin was created in 2008, Schnorr signatures were still covered by patents that didn't expire until 2008 to 2010. ECDSA was the standard, widely implemented, and patent-free. Using ECDSA allowed Bitcoin to launch without patent concerns and leverage existing cryptographic libraries. By the time Taproot was being designed in 2018 to 2020, the Schnorr patents had long expired and the advantages of Schnorr for Bitcoin's use cases were well understood. Another alternative is ECDSA, used by cryptocurrencies like Monero. ECDSA uses different elliptic curves than Bitcoin's SECP-256K1, specifically the Edwards curves, which have some nice mathematical properties. ECDSA is deterministic by design and offers simple implementations, but switching to ECDSA would have required a hard fork and would not provide as much benefit as Schnorr, which can use the same SECP-256K1 curve as ECDSA, allowing for gradual adoption. Despite its limitations, ECDSA has served Bitcoin well for over 15 years. It is well understood, has had extensive cryptanalysis, and has proven secure in practice. The transition to Schnorr signatures through Taproot represents an evolution of Bitcoin's signature scheme rather than a replacement due to security issues. ECDSA will remain supported in Bitcoin indefinitely for backward compatibility, and millions of users continue to use P2PKH and P2PKH addresses with ECDSA signatures securely every day. Signature malleability and solutions. Signature malleability was a significant issue in Bitcoin's early years. Understanding it provides insight into both ECDSA's properties and Bitcoin's evolution. Malleability refers to the ability to modify a signature or transaction in a way that makes it still valid, but changes its transaction ID. This can cause problems for certain Bitcoin applications. ECDSA signatures have an inherent malleability property. For any valid signature with R and S values, there is another valid signature with the same R value, but with S replaced by N-S, where N is the curve order. Both signatures are mathematically valid and will verify correctly, but they are different byte strings and therefore produce different transaction IDs when the transaction is hashed. This means an attacker, or even a relay node, could modify a transaction signature without invalidating it, changing the transaction ID in the process. This malleability caused practical problems. If someone is waiting for a specific transaction ID to confirm, and an attacker modifies the signature before it gets confirmed, a different transaction ID will appear in the blockchain. This could confuse payment tracking systems and make it difficult to build transactions that depend on unconfirmed parent transactions, which is necessary for payment channels and Layer 2 solutions like the Lightning Network. Bitcoin addressed this with BIP62 and BIP66, which standardized signature encoding and required low S signatures. By requiring that S must be less than or equal to N divided by 2, Bitcoin eliminates the signature malleability issue because now only one signature form is standard and will be relayed by nodes. If S is greater than N divided by 2, the signer must use N-S instead. This simple rule cuts the signature space in half and ensures each message has only one valid signature form with a given R value and private key. SegWit, introduced in 2017, provided a more comprehensive solution to transaction malleability. By moving signatures into a separate witness structure that is not included in the transaction ID calculation, SegWit makes it impossible to modify a confirmed transaction's ID by modifying its signatures. The transaction ID is calculated from only the non-witness data, so signature changes cannot affect it. This enables advanced features, like the Lightning Network, which require transaction IDs to be immutable even before confirmation. There are other sources of malleability beyond ECDSA's mathematical properties. DER encoding has some flexibility that can be exploited, such as padding values with extra leading zeros. BIP66 required strict DER encoding to eliminate these malleability vectors. There was also script sig malleability where nodes could add extra script operations that don't affect execution, which SegWit also solved by committing to the script sig via the witness program. Understanding malleability is important for anyone building Bitcoin applications. If you are implementing transaction tracking, payment channels, or complex multi-signature workflows, you need to be aware of which transaction types are malleable and structure your applications accordingly. Modern best practice is to use SegWit transaction types which are non-malleable, but millions of legacy P2PKH addresses still exist and require proper malleability handling. ECDSA implementation considerations. Implementing ECDSA correctly is challenging. Many security vulnerabilities in Bitcoin and other cryptocurrency systems have resulted from implementation errors, rather than cryptographic weaknesses. Understanding the common pitfalls and best practices is essential for anyone implementing Bitcoin transaction signing or verification. The most critical consideration is random number generation for K values. Even with RFC 6979 deterministic generation, the implementation must be correct. The HMAC-based derivation must use exactly the right inputs in the right format. Any implementation errors could result in predictable or biased K values. Even worse would be falling back to random K generation without proper randomness, which could lead to K reuse or predictable K values that allow private key extraction. Elliptic curve arithmetic must be implemented carefully to avoid timing attacks. A naive implementation might complete faster for certain values of the private key, leaking information through timing. Constant time implementations ensure that operations take the same amount of time regardless of secret values. This requires careful coding, avoiding conditional branches that depend on secret data, and using constant time selection techniques. Specialized cryptographic libraries like libsec P2PKH, which Bitcoin Core uses, have had years of expert review and optimization for security. Modular arithmetic operations, particularly modular inversion needed to compute K-inverse and S-inverse, must be correct. These operations involve extended Euclidean algorithm or other techniques. Implementation errors in modular arithmetic can lead to incorrect signatures that fail verification, or worse, signatures that reveal information about the private key. Testing with known test vectors is essential to catch these errors. DER encoding and decoding must be strict. BIP66 requires very specific DER formatting, and implementations must reject any deviations. Common errors include accepting non-minimal length encoding, accepting negative values where only positive is valid, or not checking that R and S are in the valid range. An overly permissive decoder might accept invalid signatures that other nodes would reject, causing consensus failures. Hash function implementation is usually less problematic because most developers use well-tested crypto libraries. However, you must ensure you are doing double SHA-256 in the right order and on the right data. A common error is forgetting to hash twice, or hashing the wrong serialization of the transaction, or not handling byte ordering correctly. Key management is another critical area. Private keys must be stored securely, ideally encrypted at rest. Keys should be generated from good entropy sources. HD wallet derivation per BIP32 and BIP44 must be implemented correctly to ensure keys are derived properly from the seed. Wallet backup and recovery procedures must be robust enough that users don't lose access to their funds, but secure enough that attackers can't steal keys. For production Bitcoin applications, the strong recommendation is to use well-established, thoroughly audited libraries rather than implementing ECDSA from scratch. Bitcoin Core's Libsec P2PKH library has had extensive review, optimization, and testing. It includes protections against side-channel attacks and has been battle-tested with billions of dollars of value secured by it. Similarly, for applications in other languages, use libraries that have been specifically designed for cryptocurrency use and have undergone security audits. ECDSA in script execution. Understanding how ECDSA verification integrates with Bitcoin's scripting system provides insight into Bitcoin's flexible validation mechanism. It also clarifies how signature checking works at the protocol level. The opcheck SIG opcode is where ECDSA verification happens during script execution, and understanding its behavior is important for working with Bitcoin scripts. When the Bitcoin script interpreter encounters opcheck SIG, it expects to find two items on the stack: a public key on top, and a signature below it. The opcode pops both items from the stack, performs ECDSA verification, and pushes either true or false back onto the stack, depending on whether the signature is valid. This Boolean result is then used by subsequent opcodes, or determines the final outcome of script execution. The signature must include the SIG hash type as its last byte. opcheck SIG uses this SIG hash type to determine what data to hash for verification. For SIG hash all, it hashes all inputs and outputs. For SIG hash none, it hashes all inputs but no outputs. For SIG hash single, it hashes all inputs and only the output with the same index as the current input. The anyone can pay flag can be combined with these to indicate that only the current input is hashed, not all inputs. The script engine must reconstruct the exact same serialization that was signed. It takes the transaction, modifies it according to the SIGHASH type, removes the signature being checked from the script code, and serializes it according to Bitcoin's specific format. Any deviation in this process will result in a different hash and the signature will fail to verify. This is why Bitcoin's consensus rules are so precise about serialization formats. OP-check SIG is actually quite expensive computationally compared to other script opcodes. The elliptic curve point operations required for ECDSA verification take thousands of CPU cycles, while simpler opcodes like OP-DUP or OP=verify take just a handful. To prevent denial of service attacks where an attacker creates scripts with thousands of OP-check SIG operations, Bitcoin has limits on the number of signature operations per block and per transaction. There is also OPCHECKMULTISIG, which verifies M of N multisignature schemes. This opcode takes M signatures and N public keys from the stack and checks whether M valid signatures are provided. Due to an off-by-one error in the original implementation, OPCHECKMULTISIG actually pops an extra value from the stack that it ignores, which is why you see OP0 before OP-check multisig in standard multisig scripts. This quirk was kept for backward compatibility. For P2PKH specifically, the script execution is straightforward. The script SIG pushes the signature and public key. Then, the script pub key duplicates the public key, hashes it, checks that it matches the expected hash with OP=verify, and finally runs OP-check SIG to verify the signature. If OP-check SIG returns true, and nothing has failed up to that point, the script succeeds and the input is valid. Deterministic signatures RFC 6979. RFC 6979 provides a standardized way to generate the K-value deterministically from the private key and message hash, which eliminates the need for a random number generator during signing, while still maintaining all security properties. Understanding this standard is important because it represents best practice for ECDSA implementations and solves many practical problems. The motivation for deterministic signatures is to eliminate risks associated with random number generation. As we've discussed, weak or reused K-values can lead to private key compromise. Many security failures in cryptographic systems have resulted from poor random number generation. By making K generation deterministic, we eliminate this entire class of vulnerabilities. The same private key and message will always produce the same K, and therefore the same signature, which is fine because the signature itself doesn't need to be random. RFC 6979 uses HMAC-based key derivation to generate K. The algorithm starts by initializing a value v to all 0x01 bytes and a key k to all 0x00 bytes. It then performs several iterations of HMAC-SHA-256, using the private key, message hash, and other domain parameters as inputs. The algorithm ensures that K is uniformly distributed across the valid range and appears random to anyone without the private key, even though it's deterministic. The specific steps involve repeatedly updating K and V through HMAC operations, creating a pseudo-random stream that is derived from the secret inputs. After initialization, the algorithm generates candidate K values from this stream and checks whether they are in the valid range from 1 to n-1. If a candidate is valid, it is used. Otherwise, the stream continues and another candidate is generated. This continues until a valid K is found, which typically happens on the first try. The beauty of this approach is that it is completely deterministic, so the same inputs always produce the same output, yet it is impossible for anyone without the private key to predict what K will be. The HMAC construction ensures that even tiny changes to the message hash produce completely different K values. And because the derivation depends on the private key, different private keys will produce different K values even for the same message. Deterministic signatures have additional benefits beyond security. They make testing easier because you can have test vectors with known inputs and expected outputs. They make signature generation more efficient because you don't need to access a hardware random number generator, which can be slow or unavailable in some environments. And they provide consistency, which can be useful for applications that need reproducible signatures. However, implementations must be careful to protect the HMAC computation itself against side-channel attacks. The same constant time considerations that apply to ECDSA operations also apply to the RFC 6979 key derivation. If an attacker can learn anything about K or V through timing or other side channels, they might be able to predict K values or learn information about the private key. Modern Bitcoin implementations universally use RFC 6979 for K generation. This includes Bitcoin Core, all major wallet software, and hardware wallets. The standard is also used in other cryptocurrencies that use ECDSA, making it a de facto standard across the industry. If you are implementing ECDSA signatures, you should absolutely use RFC 6979 rather than attempting random K generation. ECDSA performance considerations. ECDSA operations, particularly signature verification, represent a significant portion of the computational work involved in validating Bitcoin transactions. Understanding the performance characteristics of ECDSA helps explain various Bitcoin design decisions and optimization strategies used by implementations. Signature generation is computationally intensive, but it only needs to be done once per input by the wallet creating the transaction. The main operations are RFC 6979 key derivation involving multiple HMACSHA 256 operations, elliptic curve point multiplication to compute R, modular inverse to compute K inverse, and modular arithmetic to compute S. On modern hardware, this takes roughly 0.1 to 1 milliseconds per signature depending on the implementation and hardware. Signature verification is where performance is really crucial because every node must verify every signature in every transaction. Verification involves DER decoding, 2 elliptic curve point multiplications, one for U1 times G, and one for U2 times the public key, elliptic curve point addition to combine the results, and comparison of the resulting X coordinate with R. This is more expensive than signing because it involves 2-point multiplications. A single verification might take 0.5 to 2 milliseconds on typical hardware. This might not sound like much, but consider that Bitcoin blocks can contain thousands of transactions, and transactions can have multiple inputs, each with a signature. A typical block might have 2,000 to 3,000 signatures that must be verified. At 1 millisecond per signature, that's 2 to 3 seconds just for signature verification, not counting other validation work. This is why Bitcoin nodes benefit from fast CPUs, and why signature verification is often the bottleneck in block validation. Several optimizations are used to improve ECDSA performance. Batch verification allows for verifying multiple signatures more efficiently than verifying them individually. This is achieved by exploiting the mathematical structure of the verification equation. libsec P2PKH implements batch verification that can verify multiple signatures about 30% faster than individual verification. However, batch verification has a trade-off. If any signature in the batch is invalid, the entire batch must be re-verified individually to find the invalid one. Precomputation is another optimization technique. Verifying signatures requires computing U1 times G, and G is always the same generator point for all verifications. Implementations can precompute multiples of G and store them in tables, trading memory for speed. libsec P2PKH uses precomputation extensively and can reduce verification time significantly. Similar precomputation can be done for frequently used public keys, though this requires keeping a cache of public keys and their precomputed tables. Hardware acceleration is increasingly important for ECDSA performance. Modern CPUs have specialized instructions for large integer multiplication and addition that can speed up elliptic curve arithmetic. Some CPUs even have instructions specifically for cryptographic operations. GPU acceleration is also possible for ECDSA, particularly for batch verification of many signatures in parallel, though the overhead of transferring data to the GPU can negate the benefits for typical block sizes. The computational cost of ECDSA is one reason why transaction fees include a cost per signature operation. In Bitcoin's block weight calculation post-SegWit, signature operations in witness data are counted and contribute to the block's weight limit. This ensures that blocks with many signatures do not take excessive time to validate and helps prevent denial of service attacks where an attacker creates blocks full of signatures to slow down validation. ECDSA and hardware wallets. Hardware wallets provide an interesting case study for ECDSA implementation because they must sign transactions securely while being isolated from potentially compromised computers. Understanding how hardware wallets handle ECDSA helps illustrate both the security model and the practical challenges of implementing cryptographic operations in constrained environments. A hardware wallet is a physical device that stores private keys. It performs ECDSA signing operations internally without ever exposing those private keys to the host computer. When you want to create a transaction, your computer builds the transaction structure and sends it to the hardware wallet. The wallet verifies the transaction with the user, signs it internally, and then sends back only the signature. The private key never leaves the device. The security of this model depends on the hardware wallet correctly implementing ECDSA and not having vulnerabilities that could leak the private key through the signatures. The hardware wallet must use RFC 6979 deterministic key generation to avoid weak key values. It must implement constant-time elliptic curve arithmetic to prevent timing side channel attacks. Furthermore, it must protect against physical attacks, such as power analysis, where an attacker measures the device's power consumption during signing to learn about secret values. Hardware wallets face unique challenges compared to software implementations. They typically have limited computational power, often using microcontrollers that are far slower than desktop CPUs. They have limited memory for storing pre-computation tables or intermediate values. They must also be efficient with power consumption if battery operated. Despite these constraints, they must maintain the same security properties as software implementations and execute signatures within a reasonable time, typically under 1 second per signature, so users don't experience frustrating delays. To achieve acceptable performance, hardware wallets often use optimized elliptic curve implementations specifically designed for embedded systems. They may use different algorithms for point multiplication that trade slightly slower speeds for reduced memory usage. They typically implement RFC 6979 using hardware-accelerated HMAC operations if available. Some higher-end hardware wallets even include dedicated cryptographic coprocessors that accelerate elliptic curve operations. The transaction verification process in hardware wallets is also interesting from a security perspective. The hardware wallet must parse the transaction sent from the computer, extract relevant information, and display it to the user for verification. This includes showing the recipient addresses and amounts in a way the user can verify. The device must be careful to parse transactions correctly according to Bitcoin's exact format, because incorrect parsing could lead to the user signing a different transaction than they think they are signing. Some advanced attacks on hardware wallets target the ECDSA implementation. For example, fault injection attacks attempt to cause the device to malfunction during signing by subjecting it to voltage glitches, clock glitches, or electromagnetic interference. If an attacker can cause the device to generate two signatures with the same key value but different messages, they can extract the private key. Hardware wallets must implement countermeasures against these attacks, such as checking their own computations or using redundant computations. Despite these challenges, hardware wallets have proven to be one of the most secure ways to store Bitcoin for most users. The isolation of private keys provides strong protection against malware on the host computer, which is the most common attack vector. As long as the hardware wallet correctly implements ECDSA and users verify transactions on the device's screen before signing, the private keys remain secure even if the computer is fully compromised. ECDSA attack vectors and mitigations. While ECDSA itself is cryptographically sound, Various attack vectors exist that target implementation weaknesses or misuse of the algorithm. Understanding these attacks and their mitigations is essential for secure Bitcoin development and for evaluating the security of Bitcoin implementations. K-value reuse is the most devastating attack against ECDSA if the same K-value is ever used to sign two different messages with the same private key. An attacker can solve for the private key using simple algebra. Given two signatures with the same R value, which indicates the same K, but different message hashes, the attacker computes the difference of the two message hashes and the difference of the two S values, and divides them to recover the private key. This attack has been used successfully against real systems, including the infamous Sony PlayStation 3 hack. The mitigation is RFC 6979 deterministic K generation, which ensures K is always different for different messages. Weak K values, even if not reused, can also compromise security. If K is generated with insufficient randomness or from a biased distribution, attackers might be able to guess or brute force possible K values. If an attacker can enumerate a reasonable set of candidate K values, they can compute what the signature would be for each and check if it matches an observed signature. If they find a match, they know K and can recover the private key. This is why cryptographically secure random number generators are essential, and why RFC 6979 uses HMAC-based derivation that depends on secret values an attacker doesn't have. Timing attacks exploit variations in execution time to learn information about secret values. If an elliptic curve multiplication operation takes different amounts of time depending on the bits of the private key or K value, an attacker who can precisely measure execution time might be able to recover these secret values after observing many signatures. The mitigation involves constant time implementations. These ensure all operations take the same amount of time, regardless of secret values, by using techniques such as constant time conditional selection instead of branches. Power analysis attacks are similar to timing attacks but measure the device's power consumption during cryptographic operations. Different operations consume different amounts of power, and by correlating power consumption patterns with known parts of the computation, attackers can infer secret values. Simple power analysis or SPA uses a single power trace, while differential power analysis or DPA uses statistical techniques across many traces. Hardware wallets must implement countermeasures like power consumption randomization or redundant computations to protect against these attacks. Fault injection attacks attempt to cause hardware to malfunction during computation in ways that leak secret information. For example, if an attacker can cause a bit flip during the K generation or signature computation, the resulting invalid signature might leak information about the private key. Or as mentioned earlier, causing two signatures to use the same K allows private key extraction. Countermeasures include checking signatures after generation, using redundant computations and comparing results, and hardware-level protections against voltage and clock glitches. Social engineering and phishing attacks, while not attacks on ECDSA itself, are worth mentioning because they are common attack vectors. Attackers might try to trick users into signing malicious transactions by disguising what the transaction actually does. This is why hardware wallets display transaction details on their secure screen and require user confirmation. Users must verify the recipient address and amount before signing, especially for large transactions. Implementation bugs are a broad category that encompasses everything from simple coding errors to complex cryptographic vulnerabilities. For example, these include incorrect DER parsing that accepts invalid signatures, modular arithmetic errors that produce wrong results, missing validation of R and S values, and memory safety issues like buffer overflows in C implementations. The mitigation is thorough testing, including fuzzing, using well-audited cryptographic libraries, having security experts review code, and following best practices for secure coding. Future of ECDSA in Bitcoin. While ECDSA has served Bitcoin well since its inception, The introduction of Schnorr signatures through Taproot represents an evolution of Bitcoin's signature scheme. Understanding the future landscape helps contextualize ECDSA's continuing role and the gradual transition to newer technologies. Taproot, which was activated in November 2021, introduced Schnorr signatures as an alternative to ECDSA. Schnorr signatures have several advantages. They are more efficient, with slightly shorter signatures and faster verification. They enable signature aggregation, where multiple signatures can be combined into one, making multi-signature transactions much more efficient. They provide better privacy because Taproot transactions can make complex scripts look identical to simple payments. And they have simpler mathematical structure with provable security properties. However, ECDSA is not being deprecated or removed from Bitcoin. The transition to Schnorr is gradual and optional. Existing P2PKH and P2PKH addresses using ECDSA will continue to work indefinitely. Many users and services continue to use ECDSA-based addresses, and there is no requirement or pressure to migrate. Bitcoin's backward compatibility and support for multiple transaction types means ECDSA and Schnorr will coexist for the foreseeable future. The adoption of Taproot and Schnorr has been slower than some expected, partly because ECDSA works well and there is no urgent need to migrate for most use cases. Wallets and services need to implement Taproot support, which requires development effort and testing. Users need to be educated about the benefits. And there is a network effect where Taproot's advantages are greater when more people use it, which creates a chicken and egg adoption problem. For developers building new Bitcoin applications, the question is whether to support ECDSA, Schnorr, or both. Supporting ECDSA provides compatibility with the existing ecosystem and addresses that have been used for years. Supporting Schnorr enables advanced features like efficient multi-signature and better privacy. Supporting both maximizes compatibility and flexibility, but increases implementation complexity. The choice depends on the application's specific requirements and target users. Looking further ahead, quantum computing poses a potential long-term threat to both ECDSA and Schnorr. Schnorr's algorithm, which could theoretically run on a sufficiently large quantum computer, can solve the discrete logarithm problem efficiently. This would break both ECDSA and Schnorr. However, practical quantum computers large enough to attack Bitcoin's cryptography do not exist yet and likely will not for many years, possibly decades. The Bitcoin community has discussed post-quantum signature schemes as eventual replacements for ECDSA and Schnorr. Candidates include lattice-based signatures, hash-based signatures, and code-based signatures. However, these schemes have significant trade-offs in terms of signature size, computational cost, and maturity. Hash-based signatures like Sphinx Plus are quantum-resistant and have acceptable performance, but produce very large signatures that would bloat the blockchain. The good news is that Bitcoin's script system and upgrade mechanism allow adding new signature types without breaking existing functionality. Just as Taproot added Schnorr alongside ECDSA, a future upgrade could add post-quantum signatures as another option. Users could gradually migrate to post-quantum addresses as the technology matures and the quantum threat becomes more concrete. Bitcoin's flexibility in this regard is one of its strengths. For the near to medium term, ECDSA will remain an important part of Bitcoin's ecosystem. Millions of addresses use ECDSA, and it will continue to be supported for backward compatibility. Understanding ECDSA remains essential for Bitcoin developers and for anyone wanting to understand Bitcoin's security model deeply. The principles we have covered, the mathematical foundations, the implementation considerations, all remain relevant, even as the ecosystem evolves. ECDSA Best Practices Summary. Let's consolidate the key best practices for working with ECDSA in Bitcoin that we've discussed throughout this presentation. Following these practices is essential for implementing secure Bitcoin applications and avoiding the pitfalls that have affected other systems. First and foremost, Always use RFC 6979 deterministic K generation. Never attempt to generate K randomly unless you have access to a cryptographically secure random number generator with verified sufficient entropy. Even then, deterministic generation is safer and preferred. Never reuse K values under any circumstances. Implement K generation using well-tested libraries, rather than writing your own implementation from scratch. Use constant-time implementations for all cryptographic operations involving secret data. This includes elliptic curve point multiplication, modular arithmetic, and RFC 6979 key derivation. Avoid conditional branches based on secret values. Use constant time selection techniques when needed. Be aware that compiler optimizations might introduce timing variations, so verify that your constant time code remains constant time after compilation. Implement strict validation of all inputs and outputs. Check that R and S are in the valid range between 1 and n-1. Enforce low S signatures by requiring S to be less than or equal to n divided by 2. Use strict DER encoding and reject any signatures that don't conform exactly to the specified format. Verify that public keys are valid points on the curve before using them. Don't accept edge cases or malformed inputs hoping they'll work. Handle transaction serialization carefully and exactly according to the Bitcoin consensus rules. Use the correct byte ordering for all fields. Include the correct data when serializing for signing versus serializing for transaction ID calculation. Append the SCI hash type correctly. Test your serialization against known test vectors. A single byte wrong in serialization will cause signature verification to fail. Use established, audited cryptographic libraries rather than implementing ECDSA yourself. Bitcoin Core's libsec P2PKH is the gold standard for Bitcoin ECDSA operations. It has been extensively reviewed, optimized for security and performance, and is used by Bitcoin Core itself. Other languages have bindings to libsec P2PKH or have their own audited implementations. Do not write your own elliptic curve arithmetic unless you are a cryptography expert and have the resources for thorough security review. Implement comprehensive testing, including unit tests for individual functions, integration tests for complete signing and verification workflows, and test vectors from Bitcoin's test suite. Test edge cases like signatures with maximum and minimum valid R and S values. Test with known valid and invalid signatures. Test malformed inputs and verify they are properly rejected. Use fuzzing to find unexpected edge cases and crashes. Protect private keys with appropriate security measures. Store keys encrypted at rest. Use secure key derivation for encryption keys. Implement proper key backup and recovery procedures. Consider using hardware wallets or hardware security modules for high-value keys. Never log or display private keys in debugging output. Ensure keys are properly wiped from memory when no longer needed. For production systems, conduct security audits by qualified cryptography experts. Have your ECDSA implementation reviewed by people who understand the subtle security requirements. Participate in Bitcoin's improvement proposal process if you are making changes that affect consensus. Stay informed about security vulnerabilities and updates in the cryptographic libraries you use. Conclusion. We've taken a comprehensive journey through ECDSA's role in Bitcoin's P2PKH transactions, exploring everything from the mathematical foundations of elliptic curve cryptography to the practical implementation details that make Bitcoin secure. ECDSA is truly the cryptographic heart of Bitcoin, providing the security guarantees that enable trustless, decentralized transactions. The elegance of ECDSA lies in its asymmetry. Signing requires the private key and involves complex computations, while verification uses only the public key and produces a deterministic yes or no answer. This asymmetry is what makes Bitcoin's decentralized consensus possible. Thousands of independent nodes can verify that transactions are authorized without needing to trust any central authority or coordinate with each other. The sequence diagrams we've examined throughout this presentation show how data flows through the system, from key generation through transaction signing, network propagation, and verification by nodes. Understanding these flows helps you see Bitcoin not as a black box but as a comprehensible system built from well-defined cryptographic primitives and data structures. Security in ECDSA comes from multiple layers: the mathematical hardness of the elliptic curve discrete logarithm problem, the cryptographic strength of hash functions like SHA-256, the careful construction of signatures that bind messages to private keys without revealing those keys, and the deterministic nature of verification that ensures all nodes reach the same consensus. But security also depends critically on correct implementation. From RFC 6979K generation to constant time arithmetic to strict validation of all inputs. As Bitcoin evolves with technologies like Schnorr signatures and Taproot, ECDSA remains important, both as a foundation for understanding newer developments and as a practical signature scheme that will continue to secure billions of dollars in Bitcoin for years to come. The principles we have covered, the cryptographic foundations, the security considerations, and the implementation best practices, all remain relevant and transferable to understanding Bitcoin's continued evolution. Whether you're developing Bitcoin wallet software, building applications that interact with the blockchain, auditing Bitcoin implementations for security, or simply seeking to understand Bitcoin at a deeper level, understanding ECDSA's role in P2PKH transactions is essential knowledge. The mathematics might seem abstract, but it has very concrete implications for the security of the Bitcoin network and everyone who uses it. Thank you for your attendance. Please consider subscribing to the channel.